Good afternoon. This is CIBE 634, Surface Water Hydrology, and I'm Professor Victor Ponce and from San Diego State University, Department of Civil Engineering. The class number today is 102. It's the second lecture of the 10th week. The subject today is catchment routing. We specifically going to be talking about the time area method and the Clark unit hydrograph, two well-recognized methodologies. If I may start in here with a little story regarding these two methods, because I know many of you will recognize that I have featured these two methods in my book, in my hydrology book. A little bit of history, I think it's necessary here. In the year 1986, I'm sorry, after having been teaching in and out hydrology almost every semester for 6 years, I decided that I could write a book to ease my teaching, better for the students and so forth. So I set up to write a book. And when you write a book, you got to figure out what's the scope of the book. What are you going to cover? The idea is that I was going to write a book that was for basic undergraduate and a little bit advanced undergraduate, because we were going to cover a few items that were part of the graduate class, just because that's the way we thought we could do it. So I recall that I had a semester sabbatical and I went to Europe. I had some friends out there that were former students, and we were talking with them about the content. I wanted some advice as to what should be the content, because every hydrology procedure has 10 methods, and we can't put the 10 methods in the book because it would be too big a book. Some people have tried to do that in the name of comprehensiveness, and they have failed to sell the book, too heavy or something like this, right? So I had to choose very carefully what I was going to cover. And not only that, I had to split the book into chapters, various chapters. So I decided, because I was very big on routing at the time, 1986, I decided that I was going to do what nobody had done before, which is to cover routing in 3 chapters: reservoir routing, channel routing, and catchment routing, catchment or watershed routing. And I set them up that way because we feel, even to this day, that reservoir routing is easy, comparatively speaking, easy compared to channel routing. And then channel routing is a little bit more complex, but not as complex as catchment routing. So even though water comes from the catchment into the channel and then into the reservoir, we're going to reverse the natural order of things and talked about reservoir first, then channels, and then finally catchment routing. So that's my chapter 10. So today I'm going to cover material that it is in chapter 10 of my book. There is 4 or 5 sections in there, if I remember correctly. The first section is the hydrologic routing, and the last part of the book of that chapter is hydraulic routing. We have already covered hydraulic routing when I described the overland flow in the first part of this class. Admittedly, we didn't get into a whole lot of detail, but you got the tools and you got the gist of what overland flow is. We covered several papers on overland flow. Overland flow is kind of the technique, or rather the theory. And then when we talk about catchment routing, you're talking about the technique. So the techniques is what we're going to cover today. There is a lot of techniques and they're not easy. So I'm going to ask that you hold, as I always say, you hold on to your seat, because this is going to be a rough ride. And one of the things about this ride being rough is because perhaps for the first time, you guys are going to be looking at time and space together. And that's exactly what we're going to be doing here. We're going to be routing. Routing is the calculation of time and space together. You cannot do routing unless you're considering time. Reservoir routing is a special case where you're considering time, not space, and yet it's still called routing, because the word routing refers more than space, it refers to time. But in channel routing and in catchment routing, it's both time and space. So that means unsteady. It means non-permanent. It means equations that contain not only X and Y, as the case may be, it also contains T, the time. So it's unsteady. And we all know that unsteady flow is the most difficult thing in hydraulics. So, however, there is an issue here of how difficult this stuff is. And the fact of the matter is that the knowledge in this area has been divided for purposes of teaching into easy routing and difficult routing. The difficult routing is usually referred to as hydraulic routing, while the easy routing, relatively easy, is hydrologic routing. So we're going to start today with hydrologic routing. As a matter of fact, I'm going to cover two methods that are at the beginning of that book. There's actually 4 methods in that book in chapter 10. The first one is time area method. The second one, Clark. The third one is the cascade linear reservoirs. And the fourth one is the actual kinematic diffusion wave routing in the overland flow plain. And we already covered that a little bit. So I'm going to refer back to the time area method. First, a little bit of history. You know, when I was going to write the book and I decided to go, I was in Europe for a couple of months because it was a place that I could hide. Basically, nobody would bother me. I was just going to write the book 16 hours per day because I really wanted to get done, which I did, by the way. But I was talking to some people that I know over there and I trust their judgment. And we were looking at the various methods that one could cover in the book, which is supposed to be a beginning book or introductory book. And the time area method popped up. And I realized that I hadn't done too much work with the time area method because it was hydrologic routing. And I was basically a hydraulic router myself. But under the advice or with the advice of the people that were out there, I decided to talk or to cover the time area method at the beginning. First, because it was relatively easy. Second, because they told me that it was very important in Europe. The time area method was important in Europe. A lot of people applied it. It was very much applied in Germany and so forth. The United States, I personally do not know exactly whether it's used a lot. I know it's used, but not a whole lot. So with that caveat, I'm going to be talking about the hydraulic, or rather the time area method that begins my chapter 10. So let me go back in here. I am going to share the screen. Today, I'm going to cover the time area method and the calculator, and then we're going to talk about the Clark unit hydrograph too. Hopefully, I'll finish with the Clark unit hydrograph. These subjects are, I'm telling you, they are complex for somebody that has never heard about them. So I'm going to be kind of slow in here. If we have time, we'll get to GO9, which is more of the same, but more complex even. I don't want to scare you, but this stuff is complex. Okay, so let's go to the time area method. This is part of my book. It's 10.1, section 10.1 of my hydrology book. So we're kind of reminiscing in here the stuff that is already should be known by you guys, because this is hydrology that I teach at the undergrad level. So catchment routing refers to the calculations of flows in time and space within a catchment. The catchment could be small, it could be mid-size, or it could be large. And the issue is whether this methodology is applicable to either small, medium, and large, or large. And the answer is simple. The procedures of that are embodied in the time area method are similar to that of the rational method. They're very similar. And since the rational method is applicable to small basins less than 1 square mile, the presumption is that the time area method would extend that procedure above 1 square mile. So we claim that it could be applied through the mid-sized basin, which goes from 1 square mile to 400 square miles. That's where we technically or generally draw the limit between mid-sized basins and large basins. Large basins could be more than 400 square miles, like 1,000 or even more, longer than that. The problem, or rather the limitation of the time area method, is that it is lumped. Lumped means in a lumped procedure, you can only get one answer, one hydrograph. You cannot get 2. If you wanted to get 2, you'd have to subdivide. And if you subdivide, you have to route. You have to route channels. And that's difficult. Not too many people do it. Well, a lot of people do it, but they do it by using the HMS model. In other words, you're not getting into the nitty gritty of it. You're running a model that has already been put together for you by the Army Corps of Engineers. Not to say that that's not important. 99%, in my opinion, of the practitioners are out there running models. They're not developing models. Typically, engineers that are working for consulting firms do not develop models, simply put, because it's too expensive. That's just not the way they do their work. Okay, so granted, then you're going to be talking in routing generally, if you work for a consulting firm, in terms of the use of the model. But even to use the model, you have to understand what you're doing, right? You can't just say, I'm going to run that model and don't know anything about how the model runs. That's no good. Okay, so it's a lump method. In that way, it's kind of similar, or it has the same features that the unit hydrograph, which we discussed Monday. We started discussing Monday. So, but this is not a unit hydrograph. It's an extension of the rational method to the mid-sized catchment. So as you can see, the variety or diversity of approaches in hydrology. Okay, so let me move on in here. Methods for catchment routing are similar to those of reservoir and stream channel routing. In fact, many techniques used in reservoir and channel routing are also applicable to catchment routing. We're going to double here in various instances. We're going to talk about something, and then we're going to say you can use this for other applications, not just catchment routing. For instance, the linear reservoir concept, which is very useful and very common, is used in both reservoir and catchment routing. Kinematic wave techniques were originally developed for river routing, but later were applied to catchment routing too, later, okay? And that's a story or a history that we have to deal with later on. Methods for catchment routing are of two types, hydrologic and hydraulic, as I already said that. Hydrologic methods are relatively simple compared to the hydraulic methods. Usually they don't solve partial differential equations. They solve ordinary differential equations, only based on T, not on X. While the hydraulic methods have the full-blown capability of X and T, and even 2 dimensions and so forth. We'll have a story on that at the end of this section on the issue of applicability of a 2-dimensional hydrologic routing model. Examples of the hydrologic catchment routing methods are significantly the time area method and the cascade of linear reservoirs. Today, we're not going to talk about the cascade because the cascade comes third in position in my book, and we're only going to presumably cover the time area method and the Clark method. So the cascade will be left for next Wednesday because Monday we're busy. Hydraulic methods use kinematic or diffusion waves to simulate surface runoff within a catchment in a distributed context. And your professor has developed, I was the first one to develop the diffusion wave method for catchment dynamics, 1986. So we have contributed, I would say, quite substantially to the development of hydraulic methods in the watershed context. Right now, 30 years later, they're being applied in various instances. And I can tell you stories about that at this point, but I'm not going to because it will deviate from what we're discussing right now. Okay, so catchment routing can be parametric, meaning empirical, based on parameters that are basically pulled out of the air based on data, actually, based on data, not pulled out of the air. It's based on data, but the data has a way of having a local nature. Conceptual, that's better because it should apply everywhere, like the curve number method, or deterministic. The deterministic are based on equations of fundamental principles like mass, momentum, and energy, and therefore they are applicable on a worldwide basis. It's mechanics, and mechanics applies everywhere. Okay, the hydrograph obtained by the time area method can be routed through a linear reservoir using a storage constants derived by empirical parametric means. The cascade of linear reservoirs is a typical example of a conceptual model used in catchment routing. So as you can see me talking about this and that conceptual, parametric, cascade, etc. And right now it may be confusing, but then eventually once you practice and you learn many of these methods or several of these methods, you'll understand how they fit together in the so-called jigsaw puzzle. Okay, one thing I should say in here is the time area method does not produce storage, that is diffusion. It only convects, that is, it translates. So it's proper that we should talk about those two things right now as we start. The concepts of translation read convection or advection also. and storage, read diffusion, are central to the study of flow routing, whether it is in catchments, reservoirs, or stream channels. There's always going to be the issue. We are convecting, but are we diffusing? Or vice versa. Are we diffusing, but are we convecting? Or are we convecting and diffusing, which is the combination of two? Those are three possibilities, by the way. They are particularly important in catchment routing because they can be studied separately. Translation may be interpreted as the movement of water in a direction parallel to the channel bottom. You translate, like transport. Storage may be interpreted as a movement of water in a direction perpendicular to the channel bottom. What are we talking about here? Is the water going perpendicular to the channel bottom? And the answer is yes. If you look at it from a very large perspective, if the subject or if the wave is diffusing, it is actually moving, albeit so lightly or slightly perpendicular to the channel bottom. It's not only moving horizontally, but also vertically. Whatever it is, perpendicular to the channel bottom. So that's what we call diffusion. But because it is a second order process, it is a much smaller process than convection, which is a first order process. You know that in differential equations, you have the first order term, which is the major term, the main term, and then the second order term, which is a smaller term, usually 10% or 5%. And then even we have a third order term, which is even 1/10 of the second order. And for practical purposes, the third order term is neglected in calculations. 99% of the time, I would say that's safely. We can expound and elaborate on this and go to the fourth order. And you've heard, if you read the literature, people in the advanced procedures are talking about fourth order schemes, but those are really the realm of theory. It's too much already to get in practice into the fourth order. We're not even getting into the third order, let alone the fourth order. Okay. Long stories. There are lots of stories in regard to what I'm just saying here, but I will skip them. Okay. The translation effect can be related to runoff concentration. So let's not get confused in here. Runoff concentration, which is the rational method, it is convection. It's not diffusion. The storage effect can be simulated with linear reservoirs. A linear reservoir is a reservoir. And the reservoir, the main feature of a reservoir is that it provides diffusion. Therefore, the linear reservoir can be used to produce storage effect. Okay. So that is the mechanics of this whole thing as we get started here. So let's take a look at the time area method. Like I said, the time area method, I don't know exactly who originated the time area method. To be honest with you, I haven't gotten that far in looking at the history of this method, but I know it's been around since the 30s. So it's about 90 years old. And like I said earlier, it's much used in Europe and in Germany and so forth. The time area method of hydrologic catchment routing transforms an effective storm hydrograph into a runoff hydrograph. Let's sit down here for a minute and ponder what we're doing. The rational method transforms a block of rain into a hydrograph. It actually gives you, it gives you the hydrograph, and it's an isosceles triangle where the time to peak is at the end of the rainfall duration, effective rainfall duration, and then it drops without diffusion. It has no diffusion, and it drops, since it has no diffusion, it's peaked. So there's a peak at the end of the rainfall, and then there's a recession, which is an abrupt recession. And by the time you get to twice the duration, you get the end of the hydrograph. It's an isosceles triangle. That is the hydrograph, I should say, general hydrograph of the rational method. A lot of people don't talk about the hydrograph of the rational method because they're interested in only getting the peak. But the fact of the matter is that we do get the hydrograph. Okay. The time area method accounts only for translation. It does not include storage or diffusion because it is an extension of the rational method. You'll see it. It's kind of a way of extending the rational method for the hydrograph, not just for one block of rain, but a succession of blocks of rain. And by the way, as a matter of fact, just based on what I just said, that's a pretty smart method to get a quick answer. Unfortunately, that answer lacks diffusion. So if you're in a basin which lacks diffusion, then you're stuck because you're not getting the right answer. You're only getting part of it. And God knows what part of it, maybe 20, 30, 50%, maybe even 70%, but it's only a part of it. You're not getting the diffusion in there. So that is the time area method. All the time area methods exaggerate the response. The wider the basin, the larger the basin, the more exaggerated the response is. Why? Because the larger the basin, the more diffusion you're going to have. And the time area method does not have any way of producing that diffusion, right? So the time area method should be used with caution. Anytime we use the time area method by itself, it will always exaggerate the flow. So why people use it? Because it's simple. It's simple to understand. You can put it in an Excel sheet readily. It will take you a couple of hours to do it, and then you'll have it forever in your Excel file. So it's simple. You don't want to do that. You don't have to do that. You can go to Professor Ponce's time area method online calculator, and bingo, you get an answer in a few seconds. Okay, and we will do that today, by the way. So if necessary, the required amount of storage can be incorporated by routing the hydrograph obtained by the time area method through a linear reservoir. So this is interesting. So we're saying in here that you don't have to worry too much about it, because if you can put a linear reservoir at the end of the calculation and diffuse or store the hydrograph a little bit or a whole lot, depending on what you're going to do or what you want to do, then you get the answer, the answer. Is it the right answer? Well, it would be the right answer depending on whether the linear reservoir had the characteristics necessary to provide the diffusion that you needed. But that, boy, that's a hit and miss, because you don't really know the answer. So how could you know the properties of the reservoir that is going to produce the right answer? But do we do that? We do that all the time. We do that. People do this all the time, even though it's not 100% correct. Required amount of storage is determined by calibrating the linear reservoir constant with measured data. In other words, if you had measured data, you could actually use a trick of the equation in order to come up with the K of the linear reservoir and therefore get the right answer in terms of what the diffusion should be. If I've succeeded in confusing the heck out of you at this point, well, so be it. You're going to have to read this 2-3 times afterwards anyway. Okay. So the time area method is essentially an extension of the runoff concentration principle used in the rational method. A little bit of history in here. Let's backtrack to 1889. Prior to 1889, there was no rational method of urban hydrology. It was done hit and miss with empirical equations. God knows how. I don't even want to look in there. And then in 1889, I believe it was Quitchling, he is credited. Mr. Quitchling developed the rational method, and he called it the rational method, because it was rational. It was modeling the concentration principle, the runoff concentration principle that Professor Ponce has talked about extensively in my book. Runoff concentration is simulated by simulated by the rational method. That's why he called it rational method, because it was rational. Why? Because the other methods that were existing prior to the rational method were irrational, because they were based on empirical parameters, C&M, which you could pull out of the air and get a number, and that was not correct. Okay, so that's the story on the rationality of the rational method. So therefore, if the rational method has any rationality, and we believe it does, then the time area method also has rationality, because it's based on the rational method. However, the time area method does not have any diffusion. Now, one that does not know could argue, why are you complaining that the time area method doesn't have any diffusion, where you're readily accepting the lack of diffusion in the rational method? And the answer is, wait a second, apples and oranges. The rational method only applies to 1 square mile, while the time area method could be applied theoretically to 400, and that's quite a difference. Because if you have 400, you're going to have diffusion. If you have 1 square mile, most likely the diffusion would not be very large, because runoff diffusion depends on the slope of the basin. And the larger the basin, the smaller the slope. We know that for a fact, because the world is round. That, I hope you understand what I'm saying. The larger the basin, the lesser the overall slope, and therefore the stronger the diffusion. The stronger the diffusion. Why? Because we know the Hayami formula, which I believe I already talked up briefly to you. The Hayami formula has the slope, the driving slope of the flow in the denominator. And once the slope gets to 0, the diffusion gets to infinity, and therefore infinite diffusion means the whole wave, if there was a wave, was obliterated instantly, and it became a sea of water. Okay, so that's to explain the concept of diffusion, because it's important, because we're going to consider it and we're going to calculate it. Okay, the time area method is essentially an extension of the runoff concentration principle used in the rational method. Repetitious here. Unlike the rational method, however, the time area method can account for the temporal variation of rainfall intensity. Correct. So it is an improvement. We not only can consider the temporal variation of rainfall intensity, we can also add after the fact a little bit or as much diffusion as we want to in order to get to the right answer. And nature is helping us, because if we had a hydrograph, measured hydrograph, we can, due to a characteristic of the equation, grab, or rather find, back calculate, that's the word, back calculate the K that you need in order to put into the linear reservoir in order to provide for the correct amount of diffusion in the aftermath or the afterthought of the time area method. Okay, so the time area method is based on the concept of time area histogram, thereby its name, or therein its name, a histogram of contributing catchment subareas. To develop a time area histogram, the catchment's time of concentration is divided into a number of equal time intervals. So in here, for instance, we have a catchment. We're going to say from here to here, over here, the headwaters, it's 4 hours. 4 hours what is the time of concentration? The time of concentration is the time it would take a very small parcel of water to move from the furthermost extreme of the watershed, that means over here, to here. It is a number that a lot of people play around with it and they think they can calculate. It's a difficult number to calculate. Not only because it all varies spatially, but also varies with the frequency of the event. It varies with the frequency of the event. And it is not linear, it is curved. It's an S curve. We happen to know this subject very well, because I developed a double boomerang curve when I did my work, 1995 work in Brazil, because we figured out that the time of concentration was a double boomerang. You know what a boomerang is? Well, a double boomerang means it goes like up and down and comes back like an S. It's just, it has the shape of an S. Why? Because that is a very unique system where the flow goes from high in bank through low over bank to high over bank. And in doing that process from high in bank to low over bank to high over bank, it changes the velocity of the over bank flow, and it produces the S curve that I'm talking about, that was referred to as the double boomerang. I actually did not call it the double boomerang. I just showed the picture, or the data of the 100, actually it was 95 years of data of the flood on the upper Paraguay proved that there was that characteristic, which I thought was very unique because I had never seen it. So I decided to publish it and say, here, this is the way this river is going to behave as far as floods are concerned, and the time of concentration of the flood. Okay. Little did I know that my report was picked up immediately by an institution in Germany, and they spent 2 years studying my report as well as the official report. There was an official report and the also ran, or the other report, which was mine. And they compared both of them, and they spent a lot of time doing that, very highly qualified people. And they concluded that the official study had not followed the double boomerang curve that Professor Ponce has put into his report. So they basically chastised those guys. You didn't do a good job because you're supposed to follow what Ponce said, and you didn't. That was bad. That was one of the things why that project kind of was blown out. At any rate, that was the story. And the reason why I'm bringing that up is because it relates to the issue of how easy or how difficult it is to calculate the time of concentration. Nevertheless, people do that all the time. It's a bread and butter. You either use the Kirpich formula or the other formula, You can even go to the kinematic, theoretical kinematic time of concentration. So there's several. Or the Papadakis Kazan, it's a very good equation. I like it very much because being of theoretical shape, it is based on data. So it's got both the strength of the theory and the data. Besides, Papadakis is my colleague and friend. Actually, he passed away maybe 5-10 years ago, early. He's about my age, but he already dead 10 years ago. Takis Papadakis, originally from Greece, he became president of one of the universities out there on the East Coast. Anyway, so we calculate the time of concentration, and here we not estimated, we adopted 4. And so what we're going to do in here is we're going to do what is called the isochrones. If you would remember, iso means equal and chrones mean time in, I believe it's Greek, okay? We borrow a number of words from the Greek language, right? So isochrones means equal time. That means that these can be plotted. For this, you got to manage the time of concentration, of course, right? And the lengths and the, now this could be done by the way, now we can do it with GIS readily. And I know many of you are very adept at handling GIS. The old timers like me kind of missed it. And I honestly must confess to you that I do not handle GIS really well, because GIS started back in the middle 90s. It became very strong in the middle 90s, late 80s, middle 90s. By that time, we were already halfway through our career, so I didn't do it. So I have to lament that I don't handle GIS very well, but that's okay. That's okay. Okay, because that was not my time. Now, the time is now to do GIS. And I know you guys are good or are planning to get good at it. You can't really practice in this day and age without knowing GIS. It's a very convenient tool. Okay, so with the GIS help, we can do this easily and come up with the time area histogram. What does this mean? For instance, it means in here that the first part, 10% of the flow was contributed the first hour. Then 30% of the flow contributed the second hour, 20% of the flow the third hour, and I kind of reflect that on the shape of the basin, the way we drew it, right? You understand what I'm doing. I'm trying to explain what the procedure looks like, and I need to match the histogram with the actual graph, which is given in blue in there. Okay, so that's the isochrone delineation and the time area histogram. So once we have the time area histogram, we say in here the time interval of the effective rainfall hydrograph must be equal to the time interval, because we're going to kind of convolute. Convolution is a procedure that is used in mathematics, is properly and well-defined in mathematics. And I believe we're going to do convolution here. We may not call it convolution, but it is convolution. It's actually numerical convolution, because a convolution actually comes from an integral and so forth. It doesn't have to be numerical. It could be analytic too. So the time interval must be equal to the time interval. Both time intervals have to be equal. The time interval of the time area histogram and the time interval of the effective rainfall hydrograph. Now, the rationale of the method is that according to the runoff concentration principle, which we know says that Q is equal, peak Q is equal to I effective times A, the effective I. The partial flow Q at the end of each time interval is equal to the product of effective rainfall I times contributing area. So Q equal to IA. We know that to be a fact. That's a fact that was developed or discovered, I guess you could say, or stumbled upon, as the case may be, by Quitchling in 1889. So it's more than 100 years old. Very well accepted procedure. And by the way, we have tested experimentally in the lab, in the numerical lab, and we know that that's the way it works. The lagging and summation of the partial flows results in a runoff hydrograph for the given effective rainfall hydrograph and time area histogram. So, advantage of the time area method, besides the fact of its disadvantage that it does not include diffusion. So while the time area method accounts for runoff concentration only and does not include diffusion explicitly, it has the advantage that the catchment shape is reflected in the time area histogram. Of course, the shape of the catchment, I tried to do this the best I could here graphically, the shape of the catchment is reflected in the time area histogram. And therefore, it is going to be reflected in the result. The result is going to reflect the shape of the catchment. And that is the reason why people have become fond of this method. While it doesn't have diffusion, it does reflect the shape of the catchment. The shape of the catchment is something important. It could be very important in certain places. I have seen many, many shapes of catchments, from the typical ovoid shape, like the shape of an egg, to elongated left and right, X plus minus, et cetera, et cetera, et cetera. There was a basin in Brazil that we looked at that was like a flat eye, like it was the width was maybe 20 kilometers and the length was 700 kilometers, something like this. It was like a lying down shape, which was interesting because that effectively controls the calculation of the flow. If you're going to calculate the flow, you better introduce the shape issue in there. So nowadays, these calculations are being done with computer models, and the computer model is asking you, give me the shape, give me the dimensions, and I'll do the job for you, which is the way it should be, right? So we are introducing the shapes into the calculations. So let's take a look at at how we do this calculation. And as normal in our presentation, everything is spelled out in here. So I'm going to go not 100% detail, but I'm just going to go over the high points, and then you are left to review this thing clearly or spend more time with it later so that you can understand exactly how it is. Actually, the problem is not that difficult in here. When you present it the way I'm presenting it, it's not that difficult. You have in here you're going to do like in time, which is the column 1, and you're going to have in the blue in there, you're going to have the effective preset. Okay, so how is this going to work? Okay, let's take a look. Let's take a look at the numbers instead of the words, because I think graphically the numbers would show. It would be clearer when we do this. And by the way, this procedure that I'm going to talk to you about today, it's called convolution, and it is also very standard. In other words, this is what's done in every application. Our calculator of the time area method does precisely this. Now, you may say at this point, how did you figure that out? How did you do that? And the answer is, we know how to program. We've been programming for 40 years, actually more than 40 years, 1973. That's 49 years, okay? So we know how to do this programming thing. Okay, so what do we have in here? In the horizontal and the vertical one, that is the time in hours. 2, 3, 4, 5, 6, 7, 8, 9. Let's take a look first. We have in here, we have how many intervals of rainfall. We got 6 intervals of rainfall. 1, 2, 3, 4, 5, 6. Okay, so those 6 intervals of rainfall are going to be in here. 1, 2, 3, 4, 5, 6. Correct? So in the abscissas, or rather horizontal line in the blue, shaded blue, it's the effective rainfall. It has to be effective. You don't time area method total rainfall, because it will get confused with the infiltration. So the first thing to do, in order to apply the time area method, you got to subtract from the total rainfall the infiltrated rainfall. And that's normally done with a method such as the curve number. The curve number typically is the one that's mostly used, by the way. I would say more than 90% of the people in practice are using the curve number. There's also RAND methods out there, like the Philip, the Green and Amped, and a couple of others that the Army Corps likes to use in their models, but they're also RANDs. The curve number is prevailing, really. Okay, and we already talked about the curve number extensively. So once you apply the curve number in here, you separate the effective, and you get only effective rainfall. And I've given, in this particular problem, I've given only effective rainfall. I didn't want to talk about the curve number. Effective rainfall, it says in figure 10.2, effective rainfall. Okay, so we got the effective rainfall. So how we're going to do this? We're going to do is like this. We're going to say, we're going to take the let me see what's over here. We're going to take the histogram, which is over here, right? Notice that the histogram has 10, 30, 20, and 40. And all of those add to 100, which is the 100, the basin size is 100. Yeah, 100 kilometers square. So 10 kilometers square, 30 kilometers square, 20 kilometers square, and 40 kilometers square. By the time you add those four blocks, you get 100 kilometers square. So now we come over here. So we're going to multiply this. We're going to multiply the A times I, AI. So at the beginning is zero. You got to start at zero because this is a hydrograph. This is not a hydrograph anymore. It is a hydrograph. The hydrograph is a block of rain. The hydrograph, like here, this is the hydrograph. Over here, that's the hydrograph, effective rainfall hydrograph. There's a summation of blocks of rain, but the hydrograph is not blocks. The hydrograph starts at zero and ends at zero. So it goes like 10 by 0.5 is 5. 30 by 0.5 is 15. 20 by 0.5 is 10, and 40 by 0.5 is 20, and then we end up with a zero. Why we end up with a zero? Because it takes that much time for the flow to generate it, to change from block to hydrograph. It takes that much time. That is because that's the way this system is set up. You can think through this and find out that exactly it is correct, by the way. I'm not going to spend a lot of time trying to explain the minor details. But the point is that this is the first hydrograph that we're calculating for the 0.5. Then the second would be for the 1. That means it's double, but it is lagged. It is lagged one interval of time. That's because, why is it lag one interval of time? Because it comes over here one interval of time afterwards, right? So it has to be lagged. People could say at this point, wait a second, how do you know that that's exactly the way it matches? And the answer, it is because there's no diffusion. If it were with diffusion, which we have purposely taken out of the method, it wouldn't be. We would be mixing apples and oranges. But because we assume that there's no diffusion, then therefore this is okay. Okay. So in here, the second is 1, the third one is 2. Likewise, look at the numbers in here, corresponding. 2.20, 40, 60, 40, and this is 1.5, and this is 1, and this is 0.5. The 0.5 should be the same, but there's a lag in there. There's a lag of 5 hours. 1, 2, 3, 4, 5 hours. Let me see, 1, 2, 3, 4, 5 hours. Exactly lag of 5 hours between 1 and 6, right? So we lagged all of it. Now we're going to sum it up. We sum it all up, and we get these numbers over here. But note that we have used weird units in here. Why? Because we're talking here, the partial flows, express them in terms of kilometer square centimeter per hour, because we took the centimeter per hour and multiplied by the kilometer square. So these units are kilometer square centimeter per hour, which effectively give us a discharge. This is area L squared times L is L cubed over time is L, it's a discharge, only expressed in a somewhat odd figure. The reason why I did it this way is to show that, in fact, this whole thing is mass conserving. Why mass conserving? Every method that we route has to be mass conserving, because if it's not mass conserving, it's no good. What are you talking about, mass conserving? Do methods do not conserve? And the answer is yes. You can have in numerical hydraulics, this is numerical hydrology, as a matter of fact. But in general, in numerical methods, no matter what methods they are, short of mechanics, solid mechanics. I don't know anything about solid mechanics. I'm a fluid mechanics guy, right? In fluid mechanics, there is no method out there that could be considered to be completely 100% accurate. And there's various ways to lose accuracy. You can lose accuracy from stability, convergence, and lack of mass conservation. Beyond other things, lack of energy, lack of momentum, but that's more complicated than what we wish to get at this time. The first one is stability, convergence, and lack of mass conservation. And in this case, we are testing that, in fact, we are not conserving any mass. Are we not? Yes. The answer is yes, because this whole thing was supposed to add to 650, and it does add to 650. After proving that, in fact, this is a mass conserving method, a perfect method. When we looked at this many, many years ago, 40 years ago, we were really amazed at how numbers could behave so well. And this is only the little story, because the big story comes next Wednesday, where we're going to show something that it is so amazing that when I first discovered it, I fell in awe. I was in awe for about 3 days, not figuring out how is it that this thing works so well. And I had nothing to do with it. I just kind of discovered it. Okay, so we'll get there. We'll get there next week, next Wednesday, hopefully. So we got a 615 here. Now at the end, we not have to express the correct flow in cubic meters per second. And then we can find the conversion factor. And actually the conversion factor is 2.67, I believe. This agrees with the total effective rainfall. It's not in here, but it is 2.6. You can take the ratio of 13.9 over 5, and the answer is 2.67, I believe. Okay, so that is the correct answer there. Okay, online routing, the result is essentially the same. Yeah, online routing, the result is essentially the same. Let's take a look in here. 1 hour. Increments of rainfall intensity, there were 6, I believe. Okay. Then enter increments of effective rainfall intensity. So those increments are 0.512, 1.51, 0.5. I didn't do this early, so I should have done it, but I didn't. I forgot. 0.5, 1, 2, then 1.5, 1, and 0.5. 1.5, 1, and 0.5. And the number of increments of watershed drainage area. This is 4. And the numbers are number of increments of watershed drainage area. And the values are over here. Where is it? It's over here. 10, 30, 20, and 40. 10, 30, 20, 40. Right. No, there's a mistake. You see, you can have a mistake in it. It has to be a comma. It cannot be a period, because a period would interpret that as being a number, continuation of a number. That's not good. Okay, so we're ready to run in here. We're ready to run. So the answer of this problem was, when we looked at this, the peak was 402, right? 402.8 was the peak. And over here, and we had made a mistake. Yeah, we have made a mistake. So we have got to fix this a little bit. Let me just look at it. I was not expecting that. I should have done this earlier. But you can understand that we have made a mistake in here. 0.5, 1, and 2. Let me see that. 0.5, 1, and 2. And then we have 1.5, 1, and 0.5. 1.5, 1, and 0.5. And 4. 10, 30, 20, and 40. Okay, let me see. Not sure exactly what's going on. We did it earlier. 10, 30, 20, and 40. So 10, 20, 30, and 40. And the answer is, okay, we got a bug in here. I don't know exactly what it is, but we're not going to spend time on it. It is roughly the value, but it should be the same, by the way. So I do kind of apologize if it didn't work out on the first demonstration, but we will continue, and I'll review this later on with in more detail. So the point is that we can do this calculation and get the online routing and do it in a fraction of a second. So let's keep moving along here. So we have the time of concentration. The time of concentration is a very important subject, and we have to recognize that the limitations in calculating times of concentration, but there are various ways of doing this. And as we say in here, the time of concentration leads to an alternate way of calculating the time of concentration, provided that there's no runoff diffusion, as would be the case of a hydrograph calculated by the time area method. The time of concentration can be calculated as the difference between hydrograph time base and effective rainfall duration. So the duration and the time base. As rainfall ceases, the farthest parcels of water concentrated the catchment outlet at the time equal to the time of concentration. So this is another formula for the time of concentration. And we can also express in a slightly different form by saying that time to point of inflection is the same as the time base of the translated only hydrograph. And those are approximations, but they're good approximations because they reflect the usual situation in practice. What they mean in here is that by the time you get to measure hydrograph, there's a point of inflection. And we can assume readily that the point of inflection, which is already known, this is T sub I, is where the translated only hydrograph died. It got over there, more or less. Okay, so we can use the measured hydrograph as an approximation to the time base. So that's what I would like to say at this point on the time area method. We've extensively covered it. Yeah, your job is to review everything I said and make sure you understand everything I said. It was fast, but it needed to be done that way. And right now, in the time that we have, we got more than 15, 20 minutes here, 22 minutes. We are going to introduce the concept of a Clark unit hydrograph. Who is Clark? Clark was a gentleman working for the Army Corps of Engineers in the 1940s, and he was charged with doing all kinds of hydrologic calculations. It was at that time that the Army Corps was very busy building the large dams in the United States. Most of the large dams were built from the 20s to the 70s. It was a large and very extensive, not extensive, but great, I should say, period of dam construction, which allow us to develop. And I don't want to get too much into it, but I mean, it was very extremely important, not only for the case of supplying water to the population, but also supplying energy to the industrial machinery. And we needed to have an industrial machinery in the 1940s because we were at war in Europe. So we needed the energy, and the energy was brought in or with the help of the hydropower that was generated by the dams. And the dams had to be designed and so forth. Many, many dams at Columbia, the Colorado, all over the United States. Okay, so Clark was there, and he had a major role. He developed in 1945 the Clark unit hydrograph. And we are going to be discussing that right now. It's part of section 10.2 of my book. So let's take a look at it. I should also say at this point that a story, which is nevertheless an important story, because when I wrote this book back in the year 86, that's almost, what, 40 years ago, 86, 2006, 36 years ago. I reviewed the concept. I looked at the original paper by Clark. I had spent a lot of time looking at that paper. It was a long paper and it was very convoluted and so forth. And the whole subject is convoluted anyway, right? But we did it, and we were young and eager at that time. And I kind of discovered that Clark had not finished the work. Why didn't he finish the work? I don't know. I'm not Clark. I wasn't there. It was 1945. I wasn't even born in 1945. Okay. But the point is that Clark had an omission in there. It was not quite an omission, but it could have been done better based on concepts that we knew by the 1886, 40 years later. We thought that we could second guess Clark and do it a little better. So at that point, I didn't know what to do because I was writing the book. So the question is, should I reflect exactly what Clark said, or should I come up with a modified way of looking at Clark? And I decided to do the second one. I said, Clark was actually a bit wrong, so we're going to fix it. And we did fix it. And we came up with the Clark method in Ponce's book, which is slightly different. It's not a tremendous amount of difference, maybe 5 to 10%, but it is slightly different. It's actually a little smaller than Clark's, always smaller for the way he set it up. Okay, so that's the story. Then time went by, and the question is, which Clark is being used in practice? And let me tell you what the answer of that question is. If you're using the Army Corps model without touching it, then therefore you are using original Clark method, because the original Clark method is embedded into the model of the Army Corps. And since you cannot change it, you cannot do anything. I mean, you cannot say, oh, I want Professor Ponce's version because it's no good. It's not going to do it. That's one thing. But if you're not using the Army Corps of Engineers model, and you want to do your own model where you are going to be using the Clark method, you really have no choice but to use my method, because my method is the one that is going to take you 3 hours to learn, and the Clark is going to take 30 hours because you're going to have to read Clark, and it's not an easy job to do that and understand what he said. So basically, I submit, and I'm 100% sure that most people that are not using the Army Corps are using my method. And those that are using the Army Corps embedded into the models are using the Corps method, which is Clark, the original Clark method. Okay. We knew that there was a difference because we knew enough about routing that there was a difference in the way the routing was done. But I didn't know how much. In the back of the year 2013, we had a very smart student, part of San Diego State here, that was doing a master's. His name is Nicole Nocitelli. And I realized from the beginning, she knew her stuff. So then she was going to do a special study like a lot of people do at San Diego State. And I said, Nicole, why don't you do this? You need to write it all out and tell the story of the difference between Clark's original and Ponce's Clark. And she did it. It took her 4 months because that's usually the procedure, the semester duration. And she wrote a very beautiful paper that we are going to get into next time we meet. Nicole's paper on the comparison between the Clark original and Clark Ponce hydrographs. Okay. I already told you the application, the applicability. So there should be no issue as to which one is preferred. It depends on who you're talking to. If it's an issue of models running Army Corps, it's Clark original. And if it's not that, then it is by exclusion, Professor Ponce's Clark. So let's get into what the difference is. The procedure to derive a Clark unit hydrograph parallels that of the time area method. The only difference is that the time area method uses a hydrograph, a full hydrograph of a storm. The Clark unit hydrograph uses just an impulse because it is a unit impulse. It's a 1 inch of rainfall for any given duration which is specified. It could be ½ an inch in 2 hours, or 1 inch in 1 hour, or 1/3 of an inch in 3 hours, each hour for 3 hours, to a total of 1 inch, right? And therefore, the Clark methodology is a unit impulse. Okay, so he basically applied the time area method for a unit impulse, which is easy to do. But then he said quite correctly that calculation that he had done did not have any diffusion. So then I don't know if he invented it at the time, but he was one of the first to come up with the idea that you could run this thing through a linear reservoir and get the diffusion that you so much need. And he did that. So basically the Clark method is nothing but the application of the time area methodology, routing methodology, to a unit impulse, meaning a unit hydrograph. And then right after that, as a second step of the computation, run it through a linear reservoir of a certain K coefficient that needs to be determined for an individual case. That was it. Since the unit hydrograph calculated in this way lacks diffusion, Clark suggested that it be routed through a linear reservoir. Okay, an estimate of the linear reservoir constant is required. Otherwise, you are circling around and don't solve a problem. This can be obtained either from the tail of a measured hydrograph or by using a regionally derived formula. People that worked in this for quite a while. And if they don't have any measured hydrograph, they go and use data from neighboring sites in order to develop a regional value. This has been documented in many books, by the way. The book by my friend Vijay Singh, Dr. Singh, has a whole bunch of equations that are regionally derived for application for determining the K to be used in the Clark method. Okay, we didn't do that in our book for whatever reason. We had to cut it somewhere. Okay, the Clark method can be properly regarded as a synthetic unit hydrograph because it's coming based on some concept, which is already synthetic, and it's synthetic because it's based on data. Like the time area method, the Clark unit hydrograph has the advantage that the catchment properties, surface and so forth, are reflected in the time area histogram because he's using a time area histogram, and therefore on the shape of the unit hydrograph. This feature has contributed to the popularity of the Clark unit hydrograph in engineering practice. The popularity of the Clark unit hydrograph, I do believe, is based on the fact that the Army Corps likes it. And the Army Corps has put it in a preeminent part of their model, the HMS. The HMS, hydrologic modeling system, used to be called HEC1. If you care to listen, the HEC1 was created in 1968. And in 1998, 30 years later, they switched it and they moved into the second generation model, which was a GUI model, meaning graphical user interface, meaning Windows for those of us. And then they dropped the HEC1. So HEC1 is no longer used. It was a character cell model. And who's using character cell these days? That was good for cards, for computer cards. And I submit that you guys have never seen a computer card. Maybe you have in a museum. They went out of the wayside in the year 1980 or 79. 79 was the last time I used computer cards. And then after that, it was all the famous CRT, which ended up eventually being a flat screen. But that's another story. That's history. Okay, so it has the advantage. When using the Clark or time area method, the storage constant can be estimated from the tail of a measured hydrograph. This procedure is a fantastic procedure because it allows you to get data from a hydrograph, accurate data, without really pleading too much for it. I mean, if there is a measured hydrograph or a hydrograph that you can somehow put together, you can look at the tail, and from the tail, you're going to get the K. How is that? Because the equation is inflow minus outflow equal to the SDT. And at the point, after the point of inflection, we already talked about, after the point of inflection, the inflow is 0. So therefore, 0 minus outflow equal to the SDT. And since S is equal to KO by definition in a linear reservoir, you replace the SKO in there and you get K equal O minus O over DO dt. So in other words, the outflow at that point, at the tail of the outflow at that point is at the end of the inflow hydrograph. We more or less know that's the point of inflection, divided by the rate of change of the outflow. So those are two easily measured variables, and therefore you get the K, right? We know that. S equal KO, so put in there KO. Since K is a constant, it comes out, and K is equal to O minus O over ds dO dt. That's it. Does this procedure work? Beautifully, by the way. We've used it many times to determine the K. Once you have the K, you're home. You can do the whole thing and finish it off, okay? But then at that point, you have a choice. You either use the original Clark procedure or Professor Ponce's procedure, and we're going to talk about that later on. Okay, so we have in here the Clark method to derive a 2-hour unit hydrograph for the catchment. This is the same kind of example. And again in here, I'm going to go over this because I feel a little more comfortable, because reading all this stuff, I'm boring you to death. I'm just going to show the table that we graphically done. Obviously, you can later go and check the language and make sure that what I said was correct. But this is the procedure, step-by-step procedure. We always do that. This is a book. This is a book where you have to learn by reading, not go and have to do any big research like I had to do, spend months in the library trying to figure out what Clark had done. That was a correct statement, by the way. Not just Clark, a whole lot of people. We finally, in the case of Vedernikov, we could never figure Vedernikov out. So I didn't know what I was going to do. But finally, we were locked out because 7 years later, after Vedernikov, came Kraya from France, and Kraya explained everything that Vedernikov had done, but in simple terms that everybody can understand. So we immediately realized that we were home in terms of understanding what Vedernikov had done. Vedernikov, for some reason, was very complicated. He was so complicated that Cha, when he wrote his book in 1959, let's go back. Vedernikov, 1945, 1946, he wrote the paper in Russian. Later, it was translated into English, but the translators apparently didn't do a good job as it was difficult to understand. I had the paper, I got it in the English translation. I don't read Russian, but we couldn't make heads or tails. I mean, it was difficult. It was a lot of mechanics and it was complicated. But eventually we got a hold of Kraya, and Kraya told us in exact terms, in clear terms, what was going on. Kraya said, when the dynamic waves exceed the kinematic waves, that's when you're going to have instability, mainly the roll waves. Vedernikov didn't say that. Vedernikov just gave you an equation, and he said, well, this is the equation and that's it, go with it. So we were helpful. We were lucky that Kraya was there to clarify things. Likewise here, we're here to clarify what people have done. It should be straightforward once you read it, because it's all indicated with columns and everything else. So let's take a look at what Clark did in the table. Derivation of Clark unit hydrograph, example 10.2. first of all, we need to figure out the duration of the hydrograph. The duration is a very important concept in unit hydrograph theory because it defines the hydrograph. Suffice it to say at this point that if you say this is the unit hydrograph for this basin, it's an incomplete piece of information. You have to say this is the 2-hour unit hydrograph, or this is a 1-hour unit hydrograph, which is typical, or a 3-hour, or a 6-hour. If it's a large basin, conceivably you could say this is a 12-hour unit hydrograph. But the unit hydrograph always has a duration attached to it. You cannot define a unit hydrograph by just saying this is a unit hydrograph. Funny as it may look, that's exactly correct. So in here, for instance, use the Clark method to derive a 2-hour unit hydrograph. We have to tell you a 2-hour. Otherwise, the problem is not specified, right? So why a 2-hour in here? Because we want to do this. This is a unit hydrograph, so it's 1 centimeter. Because we're using units of SI customary, or not customary, SI units. So 1 centimeter. It could be 1 inch or 1 centimeter, but in this case, we've chosen to do it in metric, so it's 1 centimeter. So since it's a 2-hour, it would have to be 1 centimeter the first hour, the first interval, I'm sorry, half a centimeter, and then half a centimeter for the second interval. Because half a centimeter per hour will give you 1 centimeter complete in the 2 hours. Here it is, okay? So that's why we have 2. If we have 3 hours, it would have to be 3, etc., and so on and so forth. And it does get complicated, by the way. This is a clear example, but this stuff, if you're not careful, you get a beautiful hydrograph, which is totally wrong. That has happened to us, by the way. You say, oh yeah, beautiful hydrograph. This should be the way. I can't believe that it looks so nice and it's wrong. And yet it is, and yet it could be, depending on the problem. Okay, in this case, it's all nice in here. So we have, now we're going to use the same example of the previous case. Okay, we have the same example, 5, 15, 10, and 20. I remember those numbers with the 0.5. And then here with the 0.5. But here we're going to lag it 1 hour because it occurs in the second hour. This is 2-hour hydrograph. Okay, so the second hour, we lag it 1 hour and we get it over here, right? And we sum it. Let's not forget at this point that we are talking in terms of units of kilometer square centimeter per hour. Why did I do this? Nobody does this. I did it for clarity and because I wanted to verify, in fact, that there was mass conservation. We've been looking at mass conservation problems since 1973 when I signed up at Colorado State. One of the first things that happened to us, besides other things that were also important, was the mass conservation. And therefore, we were always not stressed, but we were always considering the possibility that we may have an equation or a method that does not have mass conservation. As a matter of fact, in 1975, when Michael Abbott, who has been widely considered to be the father of computational hydraulics, at least in Europe, because he was English, working out of, I believe, Denmark. He came to Colorado State University in 1975, and he gave a lecture, which I attended, of course. I was a student at the time. He was a well-known guy. He had written a couple of books and so on and so forth. And Michael Abbott said something like this, if I remember correctly. What he said was that models can gain mass and energy and momentum. If they're not properly built, properly constructed, they could do it. And this gain, false gain, could be so large as to obliterate the calculation and run it, how can I say, total in error. And we have shown that that is in fact the case when one is not careful and does not follow the proper procedures and rules in developing models. Who develops models these days? And the answer is very few people, because it's expensive. Typically, the people that develop models are those that are studying for either masters or PhDs at the universities. How many? Many universities across the United States and around the world have models of all kinds. So those are the people that go out there to study and develop. Then after that, you get out of it and then you go to practice in engineering, in the engineering field, and you probably are not going to develop it. But you know how it's done. That's good. You should know the basics and you should know profoundly where things came from. Now, those of you like me that continue on to do a an educational and research career could continue to develop models, because that's part of what we do. Okay, so if you get into a situation like mine, for instance, then you could still continue to do that, but not in professional practice of the in the consulting firms. The consulting firms don't do research. Everybody knows that. Why? Because it's not their job, really. I don't want to get into that. Okay, so partial flows and sums, then we do sum it up. We get the kilometer square centimeter per hour. And then in here, we are going to apply the concept of linear reservoir. In order to do that, I don't have the time to get in there, but I'm going to recommend that you go back and read chapter 8 of my book, because we're going to need it. We're going to need it next time we meet, next Wednesday. I'm going to be throwing stuff at you that you're going to go like, oh, what is this? Never seen this, because you never routed a reservoir. So in order to route a reservoir, you got to go back to my book, chapter 8, and read that part that says routing reservoirs, because that's basically what we have in here. So if you have not seen this before, you won't be able to relate to it. We have the C0, the C1, the C2, etc., I2, I1, and O1. And then we get these numbers in here from the mechanics, or the mechanism, I guess the procedure for routing through reservoirs. And we get it over here on the sum over here. Note that a reservoir has the avowed purpose of diffusing the flow. So let's see if this reservoir diffused the flow. Okay. By the way, before we get in there, one, we have to have calculated the K. And we did calculate the K over here. Oh, the K is given. The K is equal to 2. So when they give you the K, then you got to figure out what the delta T over K is. The K is 2 and the delta T is equal to 1. So delta T over K is 1/2, from which the tables show, because there's tables for and equations, show that the coefficients of routing are C0 1/5, C1 1/5, and C2 3/5, because these three coefficients are routing coefficients, reservoir routing coefficients, have to add up to 1, and they do in fact add up to 1, as you can see. So these are the coefficients that go in here, and then you go in a square grid and you do the routing, as I already told you how it's done, and you get the sum. Now note that the inflow to this reservoir, the peak of the inflow was 30, right? That's the peak of the inflow. But the peak of the outflow is over here, is 21. Did this reservoir diffuse the flow? Absolutely. It reduced the 30 to 21. Not only did it reduce the 30 to 21, but the time base of the initial, of the inflow hydrograph was 1, 2, 3, 4, 5, 6 hours. That was a time base. In other words, it went from 0 to 0 in 6 hours. Over here in the outflow, it started at 0, and by the time it got to 20, it barely had made it back to 0.01, which is close to 0. So it went from 6 hours time base of the inflow hydrograph to 20 hours, barely 20 hours. Not barely, a little more than 20 hours. Let's say 20, 21 hours. If I had done this one more time, I would probably have gotten into 0.00. But I didn't know, I didn't want to do it more than that. I know that everybody would understand that it had to go back to 0, 0. Okay, so we have proven that by using this with a K equal 2, we have actually diffused the hydrograph, which is exactly what Clark wanted to do. So how is it that Clark said, or we said, that the K should be equal to 2? That is experience, that is from having done some of the calculations, or you can do a trial for demo purposes, or whatever it is. But this has to be a certain number. And it cannot be too small, by the way. Because if it's too small, it could get to the point where it reflects that there's no reservoir. The reservoir is negative. And if the reservoir is negative, then you're going to blow up the computation. So there's a standard for this. And the K, the delta T over K should not be greater than 2. So in this case, it's 1/2, which is cool. You could still have 1, will get less diffusion, but you still work. 1.5 will work, but 2 will start to jump around and give you trash, garbage. If you use 3 or 4, it'll blow up on your face. The calculation will blow up on, excuse me, it will blow up. You'll realize that you have made a mistake. And if you don't know what you're talking or you're doing, you wonder, where did I make a mistake? The answer is that the model, the method cannot work with delta T over K values greater than 2. That's in chapter 8 of my book, by the way, explicitly stated that way. So I'm going to stop in here. Yeah, I'm going to ask you to run the routing. I'm not going to do it now. First of all, I have a good excuse. We ran out of time. Okay, but it works. And I'm going to check on that other one to find out what exactly went wrong in the demo. Okay, well, thank you very much. At this point, I am going to cut down the share, and remind you that today is Wednesday. Monday, we're going to meet 7.5-minute presentation by each one of you, cover the 75 minutes that we have allotted. And I will be grading on content, on presentation, on everything, grammar, the whole thing. You're supposed to know your grammar. If you don't, then you're going to have to pay for it later on. So you might as well learn it while you're at school. I didn't meant to say that you didn't know it. I'm just saying, I'm kind of warning you. And I know from the work that I've seen from a few of you, you seem to be lacking a little bit. You have to spend a little more time in the writing and the grammar.